Well, welcome to the first ever Cosmology talk. I'm here with Kit Gallagher, who was a co-author or first author in a paper I found very interesting earlier in the year.
Co-author.
Co-author.
Not first author.
Okay.
Unfortunately.
Called Viable Gauge Choices in Cosmologies with Nonlinear Structures, which I found very interesting because it seemed to have interesting things to say about what gauges are and are not usable in different circumstances, especially in the context of in-body simulations and things like that. But Kit is the expert, so I'll leave it to him. He's currently a PhD student at it's Queen Mary, right?
Yeah, Queen Mary.
Queen Mary, and finishing up and looking for postdocs. So if you find this interesting, give him a look. So the first thing that would be good for you to share is basically just a short summary of what it actually is that you guys have done, and
Okay, so at the heart of it, what we really did was compared the gauge problem, or the differences in the gauge problems, in two different approaches to approximating solutions to the Einstein field equations. So in cosmology, I think the approximation scheme that people are most familiar with is cosmological perturbation theory. And generically, as a theoretical scheme, you should think of cosmological perturbation theory as being valid on all scales, provided that all the quantities in your approximation scheme are small. And the other approach is Post-Newtonian gravity, which has a much less of a rich history of being used in cosmology, but has been constantly used in things like astrophysical gravity and binary black hole mergers. Post-Newtonian gravity is only valid on small scales. So in cosmology, that would be scales of about less than 100 megaparsecs, so roughly the size of kind of the largest known gravitationally bound structures in the universe. But the key advantage that the post-Newtonian expansion has is that you can use it when density contrasts are of order 1. So I think you can see already that there might be different circumstances in which one was wanting to construct a cosmological model that different approximation schemes might be more or less useful. So generically, when you do an approximation to the field equations, you encounter what's referred to as a gauge problem. And the gauge problem is a result of residual coordinate freedom that is left over from the freedom to choose your coordinates in the full theory. And specifically, this residual coordinate freedom manifests as a non-uniqueness of map between your background manifold and your perturbed manifold. And what happens is that you're forced to, at some point, make an arbitrary choice. Now,
and just in the context of cosmology, the background manifold will almost always be an FRW
Friedman.
metric.
Yeah, or Friedman. I mean, you can do this using you can do this using any exact solution, but in cosmology, it's always going to be Friedman or Bianchi if you want to get really, really wacky.
Right. And then the perturbed one is then that with perturbations.
Exactly. The perturbed space-time is some inhomogeneous space-time, which is hopefully in some sense close to the exact solution.
And the exact same space-time can be written with a different set of perturbations, and that's the non-uniqueness problem.
Yeah, exactly. So the point is that there's no unique way to take a point on the exact solution, say Friedman, and then map it to a point on this Friedman with perturbations. Yeah. Because there's an infinite number of coordinate systems which are all close to each other by some small amount, which give you equivalent results. And what happens then is you're obliged to make some kind of choice, and specifically this usually manifests itself as a reduction of the number of degrees of freedom in your metric from 10 down to 6. Now, this sort of thing is like very common in physics in general. So you encounter these kind of problems in electromagnetism, and generally speaking, all gauges are equally valid. So what physicists usually do is they choose a set of coordinates which is particularly convenient for answering a problem at hand. However, our point really was that if we want to be comparing gauge problems across two different sets of approximations to general relativity, the gauge problems in those different formulations are not identical, which means that something that might be a gauge equivalent in cosmological perturbation theory, it might have some equivalent formulation in the post-Newtonian sector, which is not equivalent to something that was a gauge transformation away in the cosmological perturbation theory approximation. So if you want to do things like calculations in cosmological perturbation theory and try and extend them into the nonlinear regime, which is something that some people do, then you need to be a little bit careful as to which gauges you're using, and to check that they're still also valid in the post-Newtonian approximation scheme. Because if they're not, then you run the risk of having chosen a coordinate system which is no longer a gauge transformation away from the other coordinate systems that you could have potentially chosen. And you could be then misinterpreting some of the results that you calculate.
And this is because some of the gauge quantities have become large, such as the density contrast.
Yeah, exactly. Or usually sometimes it can be because you chose a quantity that was gauge invariant in one formulation, but not in the other formulation to be zero or something like that. Okay. But what it turns out is that there is a subset of gauges which are viable in both expansions simultaneously.
Okay.
And that if you want to ask questions about cosmologies that have nonlinear structures, then it's this subset of gauges that you should be using to ask those questions. So,
and can I ask you, just flagging this up now so that we both remember, to maybe share at some point, and I put it in the description or something, a good reference for gauge perturbation theory and a good reference for post-Newtonian theory, assuming that people kind of aren't familiar. So maybe there are people coming from the post-Newtonian side, and maybe there are people coming from the perturbation theory side.
So if you want to know more about cosmological perturbation theory, probably the paper by Malik and Wands. It's a big review article that has almost everything that you need to know in it. Or for post-Newtonian gravity, there's a book by Cliff Will and Eric Poisson, which covers the lot in sort of obscene, gory amounts of detail.
Okay, with a nice introduction as well, or
for
people who don't want the gory detail.
Oh, it's brilliant! It's brilliant stuff. But it's. I mean, Poisson and Will's book is like thousands of pages long and has only one chapter on post-Newtonian.
Okay. I see. So the chapter itself is
or you can look in MTW.
Misna Thornham Wheeler.
Yeah, it's absolute classic.
Cool.
Anyway,
so carry on.
But the point was that, and I think we should be careful to say this, is that we're not saying that choosing some gauge, for example, like a co-moving synchronous gauge in cosmology, is like a bad gauge choice. It depends on the question that you're asking. And if you want to ask questions about cosmologies that do have nonlinear structures on small scales, then you need to be a little bit more careful about which gauges you choose, and you need to have them be in the subset of the gauges that are applicable in both approximation schemes. I guess another question you can probably anticipate is, why would you do this? Like, why do you care? Like, what's the point?
Very good question.
So I guess if we take a large scales view of that question, then the answer is that next generation galaxy surveys are going to require more realistic theoretical modeling than people have been doing in the past. So I think a lot of the old modeling in cosmology relied heavily on cosmological perturbation theory, and in cosmological perturbation theory, the critical assumption that you're forced into making is that all of the deviations away from Friedman are small. And not only are they small, but they're all small and they all have exactly the same sort of order of smallness or magnitude. And as these next gen surveys they're going to obviously extend our
Sorry, can I just interrupt to ask
yeah.
a question? So when you say the same order, you mean like the metric perturbations and the density perturbations and the velocity perturbations are being assumed to, if one of them is 10 to the minus 3, they're all 10 to the minus 3 in some dimensionless unit.
Yeah, exactly. Okay. So I mean, the way we wrote things in the paper, I'll just try this, is
sure. Yep.
We have some situation where we have a density contrast delta, which is the same size as a velocity perturbation, which is the same size as a metric perturbation,
okay,
which is all we'll call epsilon, where epsilon is where epsilon is like, say, 10 to the minus 4.
Okay.
And in cosmological perturbation theory, you're kind of forced into this state of affairs where all these quantities, they have the same order of smallness. Now, one of the things that the next gen surveys are going to do is they're going to increase the resolution of our observations on small scales. And we know that in the real universe, particularly once you get down below scales of about 100 megaparsecs, that this assumption stops holding true. And that below 100 megaparsecs, areas where the density contrast can in fact be of order 1 are quite commonplace. And to try and sort of combat this problem, some new theoretical approaches have tried to incorporate some post-Newtonian ideas. So I think there was an approach by some guys called Milio and Marco Bruni called the post-Friedman. And that was based on trying to extrapolate some post-Newtonian calculations up onto larger and larger scales. And I myself worked on something called two-parameter perturbation theory, where we tried to sort of simultaneously do a cosmological perturbation theory expansion and some post-Newtonian expansion. And other people have tried to do things like take the results from cosmological perturbation theory, go to higher order, and then extrapolate those results down in the in this sort of non-linear regime. But the point, as we tried to make clear in my earlier speech, is that when you do this, you need to be very careful that the coordinate systems that you're comparing results in, say if you did some calculations in post-Newtonian gravity for the small scale stuff, and then you wanted to infer something about larger scales using some corresponding cosmological perturbation theory expansion, you need to be extremely careful that the coordinate systems that you're using, that the coordinates mean the same thing in each case.
So is this, for example, I've run an in-body simulation that maybe has a full size of a few gigaparsecs, so it is actually getting quite large. And what you're essentially saying is, if I want to know, I don't know, the density profile around galaxies, I don't really have to worry. But if I want to know the correlation function between galaxies on the bigger than gigaparsec scale, that I need to sort of be a little bit careful about what gauge I'm assuming my in-body simulation was running in.
Yeah, a little bit. So on that theme, that this is an approach that some people are putting into practice now, is trying to extract relativistic results on larger scales from some simulations. So something there's, again, we're sort of jumping ahead of ourselves already here, but something that some people are doing is trying to use these gauge transformations to say they set the paths of all the particles in their n-body simulations to be following paths such that the outcome would be predicted by the purely nonlinear Newtonian equations of motion, but then redefining all the variables in those equations such as they were coordinates from some corresponding relativistic problem.
I see.
And in that way, they solve all the nonlinearity on the short scales just using this Newtonian using this Newtonian simulation, but somehow they're extracting some of this more relativistic large-scale information.
Yeah.
Now, and it's a really fascinating approach, but what we wanted to point out is that you do need to be quite careful when you try and apply these sorts of ideas and connecting large scales and small scales, that you haven't broken any of the rules.
Cool. So definitely at some point before we finish, we would be nice if we could say what the care is that people need to take. So, but yeah,
we'll get to that. Don't you worry.
Well, maybe I'm not sure how much time. It might be that Zoom only lets us record for 40 minutes, but we'll cross that bridge if Zoom cancels us.
Okay. So I think also it's important to maybe just point out why nobody did this before, because it does seem like quite an obvious thing to do, because the calculations that we did in the paper, they're not particularly challenging or difficult, and they're almost kind of trivial observations. But it's really because using post-Newtonian ideas in cosmology is kind of a new thing to do, and people haven't really just cottoned on to that's a different way that you might try to attack this problem of short-scale nonlinear density contrasts. Anyway, so I guess if I was to give you two takeaways, the first takeaway is that you should be very careful doing gauge transformations when nonlinear if you're trying to construct a model where nonlinear structures are in the model. And you should be careful trying to extrapolate results from small scales to large scales in such cases. And but there are some specific gauges where you can do those kind of things, and why that is we'll come to explain shortly.
Cool.
So we could perhaps go to the slides.
Yeah.
Okay, so I'm just going to share my screen. Okay. Is that coming through?
For me, yeah. I mean, all I see is the title, but I assume that the equations show up as you move through the slides.
Okay, exactly. So more technically speaking, in cosmological perturbation theory, this is the sort of thing we're trying to model. We have some inhomogeneous space-time where the metric is just g mu nu, and we're trying to construct a model of that by taking some g bar mu nu, which is like an exact solution, and then adding some small perturbations.
Yeah.
And so the size of g bar is usually expected to be around order 1, and then the size of the perturbations might be something like 10 to the minus 4, 10 to the minus 5. And we do the same thing to the stress energy tensor as we did to the metric.
Fair enough. Yep.
We expect that the background equations they exactly solve the background Einstein equations, so the background metric, the background stress energy tensor. And then you can look at some linear order equations, which will then provide you with a linear first approximation to a supposedly nonlinear solution. And you can keep doing this order by order, and you hope that if you add up all the order by order contributions, that you end up with something that does converge to the full Einstein equation.
Right.
Now, as I was saying before, generically, when you do these sorts of things in general relativity, you encounter some conceptual problems. And so the first conceptual problem really is that the quantities g bar mu nu and delta g mu nu, they live on fundamentally different manifolds. So g bar mu nu is an exact solution. It lives on some manifold, and delta g mu, or the perturbed spacetime is a completely different manifold. In fact, it's not even clear what spacetime delta g mu nu by itself even lives on.
I was wondering about that. Yeah.
It's totally unclear. So what you have to do.
The point there being that it's g bar mu nu plus delta g mu nu that is the actual full spacetime, and g mu nu is itself a manifold on a homogeneous spacetime, but but the additional delta G
Yeah,
is not itself.
it's not clear what space-time that thing even lives on. But you can do this type of thing as long as you are equipped with a map that takes you from a point in G bar mu nu to the perturbed space-time, because that then allows you to consider the delta G mu nu as being like a function that lives on the G bar mu nu space-time. So you can then do things like add and subtract background quantities from perturbed quantities in a consistent way. The problem, so yeah, that's the map that takes you from m bar to n, etc.
Yep.
But the problem is that if delta G mu nu is small, in some sense, so small like 10 to the minus 4, that there are actually an infinite number of these maps which will give you equivalent results. So there's no unique choice of mapping from the exact space-time to the perturbed space-time. And in some sense, you can think about this as there existing a set of coordinate transformations, or infinitesimal coordinate transformations. So if you have some point x mu on the exact space-time, then you can add this infinitesimal quantity chi mu to it and calculate results, and physical quantities won't change. And if you do that, then all of the tensor quantities that you define on your exact space-time as well, they will also have associated changes. And you can calculate those changes by using the exponential map. So that's that t dash equals e to the Lie derivative of that psi mu multiplied by t.
I think that might lose people who haven't done perturbation theory, but so long as it's not super important, we can carry on.
Don't worry about it. The point is that there are an infinite number of these maps, and that choosing a map is equivalent to choosing a psi mu here, where psi mu is some infinitesimal quantity. It's equivalent to doing some infinitesimal coordinate transformation. So what we want to do is then decompose delta G mu nu into its different constituent parts, and see how those different parts of the metric will transform under a generic gauge transformation. So usually the way that we decompose the metric in cosmology is like this. So the naught component of the perturbed metric just has a scalar contribution, which we're calling phi here, and where that a is just the scale factor from Friedman. And then the naught I component has some part that's constructed from a derivative of a scalar, and then some part that's an inherent vector mode. So it's a divergence-free vector. And then the ij component of the metric will have a scalar part, which is that psi, and then another scalar part, which is built from derivatives, which is like the e with two derivatives of ij. And then there'll be a vector part f and a tensor part h as well. Now, so what I've got here are some transformations for the full tensor G mu nu under that exponential map. So the maths looks a bit complicated, but you can just look up the formula for what a Lie derivative is, and these are the things that come out. But the important thing that we learn from this exercise is that the size of the chi mu, which we refer to, so it's that infinitesimal coordinate transformation, but we refer to that vector chi mu as a gauge generator. But the size of the gauge generator has to be the same size as the metric perturbations here. And that has to be the case, otherwise you're liable to generate some quantity that could potentially be large.
I think
does that make sense? So if you look at those equations here, you can imagine splitting the G naught naught into some G bar naught naught and some delta G naught naught. But if you were adding something that was the same size as G bar naught naught, you run the risk of adding something to your background. So
Yeah,
you would
yeah.
end up with a space-time that wouldn't be perturbatively close to Friedmann anymore.
Right. And because Einstein equations couple the stress energy tensor to the metric, and because the coordinate system is what's deciding the metric, if any of the quantities aren't of order epsilon, then because these are related to each other via the Einstein equation and such, that would mean that there's the risk that that quantity that isn't of order epsilon is actually going to be a part of, so suppose it was the density contrast, then because of Einstein's equations, you would have that the metric equals some function of the density contrast because it's part of the stress energy tensor. But if that's not of order epsilon, then the metric will have some contribution that is also not of order epsilon. Is that the sort of point?
So that
an unrelated
is
thing?
the sort of point, but that's also a little bit further down the chain of logic. So here we're just looking at the size of the gauge generators.
Okay.
And the point here is that if my gauge generators were not at least as small as epsilon, then I would be liable to potentially add something to my background quantities that was the same size as the background quantities, which would mean that I could then I could supposedly gauge myself into some space-time which was not the original Friedmann that I started with, at least at the background level.
Okay, and that then is just as simple as the fact that if I look at the bottom left-hand corner here, all three metric quantities, G naught, G naught I, and G naught, and for Gij, all depend on, what is it, psi? I always get this confused. Psi, mu. Yeah, okay,
exactly.
Cool.
Right. Chi, psi, yeah. Oh, I don't know.
Yeah, I think it's either psi or zeta, but yeah.
Zeta's the other one. Zeta's the other one that's coming later.
Okay, it's
so
xi
this
then.
was xi. Yeah, I never know how to pronounce it. Anyway, so that's the sort of the structure of the gauge problem in cosmological perturbation theory. Now, what happens in post-Newtonian gravity? Still an approximation to the Einstein equations, but a different type of approximation, and the corresponding gauge problem is slightly different. So, first of all, post-Newtonian gravity is well equipped to deal with large density contrasts, and this is kind of well established and quite intuitive in a way. So if you, in particular, people have used post-Newtonian gravity to do calculations of things like binary black hole inspirals. So here I've got the advance of the perihelion of Mercury, but you can imagine that a black hole binary inspiral is a system which has a density of 0 almost everywhere, apart from at the black hole where the density is quite large. But it seems that even though that system is quite potentially dangerous, you can still use post-Newtonian gravity to get decent results, at least for the sort of inspiral phase.
Sure.
So the first question is, like, what are the conditions under which we can do a post-Newtonian expansion? And the first condition is that the length scales of your problem are no larger, at least in cosmology, let's say about 100 megaparsecs. And it might seem a bit arbitrary. Where did this number 100 megaparsecs come from? The way you find it is actually related to the second condition. So the second condition is that the typical velocities of the system are small compared to the speed of light. So there I've got the dimensionless peculiar velocity v being of order eta, which is of order 10 to the minus 2. So if you take the characteristic length scale in cosmology to be the particle horizon, then in particular, this scale of about 100 megaparsecs is the scale that ends up coming out when you apply this kind of logic. So
is that literally that if I put in like the Hubble expansion, the velocities, or is this the peculiar velocities or just any velocity?
Peculiar velocities.
Okay.
So this is basically the scale at which effects due to the finite propagation speed of light are kind of still negligible in cosmology. Like so, and it's precisely this scale where you tend to get things like virialized structures.
So this has got nothing to do with
general
relativity. This is actually like a special relativity limit, essentially.
So what the reason we call it a post-Newtonian expansion is that the first leading order terms that arise in it give you back exactly Newtonian gravity, but then you can calculate the subsequent corrections that would then approximate like a true GR solution.
Yeah, but this limit of 100 megaparsec is when special relativistic effects should be taken into account that post-Newtonian gravity can't. Okay. Okay.
It is kind of for that reason. I'll go into
So
it.
it's not like a curvature scale or a horizon scale. It's a propagation of information scale.
I can. Yeah, it is a propagation of information scale, and
okay.
I can probably give you a better intuition as to why on the next slide with
cool.
another diagram.
Yeah.
But the final condition for the applicability of the post-Newtonian expansion is that the gravitational field is everywhere weak. And not only is the gravitational field weak, it's weak like eta squared. Mm-hmm. So that would be about 10 to the minus 4. And again, if you think about the virial theorem, so that's saying the gravitational potential energy is about like half mv squared. Mm-hmm. That's kind of where this is coming from. And you can also think about this in contrast to the situation in cosmological perturbation theory, where the gravitational potential was about 10 to the minus 4, but the peculiar velocity was also about 10 to the minus 4. So you can see already that something's starting to happen, which is that there's a different hierarchy in the sizes of the quantities in your expansion.
Oh, sure. And I mean, your zeroth condition is that it's capable of dealing with large density contrasts. So that's completely different to perturbation theory.
Exactly. So small velocities and weak fields, these conditions, these approximation conditions, they have mathematical consequences. And the first and most important mathematical consequence is that now when you consider taking time derivatives of quantities in a post-Newtonian expansion, your time derivatives will tend to be a factor of eta smaller than your spatial derivatives. And you can see that just by rearranging the relation V over C is like eta using the chain rule.
Okay.
Does that make sense?
Yeah, I mean, it looks like a pretty standard chain rule.
Yeah, okay. That makes sense. Okay. And when you do this, you've changed the structure of your equation system fundamentally. So if the Einstein equations in normal sense are wave equations, then you can imagine some equation with 2 time derivatives on the left-hand side and 2 spatial derivatives on the right-hand side. If my time derivatives are small compared to my spatial derivatives, then my equation, which has 2 time derivatives on the left-hand side, well, they just get neglected and you're just left with 2 spatial derivatives equals 0. So what happens is that instead of solving wave equations, or with some constraints, which is what happens in cosmological perturbation theory, you end up solving Poisson equations at every order. And to answer your questions earlier about why you are restricted to a particular scale, so you can think about a solution to the wave equation as being the integral of some retarded Green's function over the past light cone. That's just like a mathematical formalism. You can just write down some formal solution. Now, what you're doing when you change your structure from wave equations to Poisson equations is you're taking the area on that past light cone that is labeled as n there. So that's
right.
That light-like surface.
Do you have a cursor that you can move over that?
No.
I can do. I'm not sure if I'm.
I have no cursor.
Okay. Hopefully, I'm doing something that just got recorded, but if not, then it's at the very bottom of the screen. Everyone can see it.
You can see that diagonal shaded patch called N, and that's a light-like surface over which you integrate the retarded Green's function.
Okay.
Now, when you change your structure of wave equations to Poisson equations, what you're really doing is you're changing the domain of that integration to be the flat space-like surface, which is labeled M.
Okay.
Now, just intuitively, I think this should give you a good sense of why you can only really use this post-Newtonian expansion on these short scales. And it's because when scales are small relative to the speed of light, the diagonal part, the edges of it are extremely close to the space-like surface. But the larger you make this domain, the larger the discrepancy between each of the edges of the surface, if that makes sense.
Yeah, it does. I mean, it might take a bit more thinking to sink into a super intuitive level, but yeah, it makes sense that those two surfaces will be close to each other over smaller distances.
The smaller I make them, the less discrepancy there is between the one on the light cone and the one that's space-like.
Sure.
And if I make them larger, the discrepancies will become larger precisely due to the finite propagation speed of the speed of light. Mm-hmm. And all this mathematical consequence. So this in turn manifests in two more ways, which are that your matter quantities and your metric perturbations are now forced into this hierarchy of having different sizes compared to each other. So you can see that there, that the peculiar velocity is size eta, and the energy density, and note that this is the energy density, not the density contrast, will be about size eta squared, which is roughly the same size as the leading order gravitational potential, which will also be about eta squared. And then the vector perturbation will be about eta cubed, and the tensor perturbation will be about eta to the power of 4.
So this is, if this is the density, this is confusing me, because you said on the last slide density contrast could be big.
Exactly. So this is not the density, right? This is the density, but this is not the density contrast, right? So this density, you can...
So if my density is of order 10 to the minus 5, but then it fluctuates by of order 10 to the minus 5, then the density contrast is of order 1.
Exactly. So what you can do is separate this density into some...
I'm not 100% sure anyone can see what you're doing, because I think that they might only see the slide. I can see a very small version of what you just wrote.
Okay, don't worry. The point is that here I haven't separated my density into a homogeneous and inhomogeneous part yet.
Okay. So what does it mean to say that a density is small? Like it doesn't, it has a dimension, right? Like a...
So currently at this point, that quantity should be like eta squared divided by the 100 megaparsec scale that we introduced squared.
Okay, with some factors of G or M Planck to make it the right unit.
Which I have judiciously set to 1 already.
And I guess you also set C to 1 when you did this chain rule thing. Okay.
Yes, I'm saying I'm choosing sensible units. Okay. But yeah, you're right. This quantity does have units. But what you'll find is that in the field equations, so you can consider two spatial derivatives of a leading order Newtonian gravitational potential.
Yes.
The gravitational potential doesn't have any units, but two spatial derivatives of it does have units, and it has precisely the same units as that energy density.
Okay.
So, and what you find is that those are the quantities that will turn up in the field equations together, which is why I've written the similar to sign. But you're correct in saying that I should be careful about assigning sizes to quantities with units.
But here, phi and psi are perturbations.
Yeah, they're dimensionless.
But they're the perturbations of the FIW metric, not the metric quantity itself.
They're the leading order gravitational perturbations.
Delta G naught naught rather than G naught naught.
Yeah, delta G naught naught and delta G I J. But the second consequence is also that the gauge generators in post-Newtonian gravity take on specific sizes. So the spatial and time-like components of the gauge generators have different sizes, and you can remember that this is quite strongly in contrast to what happens in cosmological perturbation theory, where both were just the same size and they were the size of the perturbations, which was epsilon. So you can see that the corresponding gauge problems are going to be slightly different now. Does that make sense?
A little bit. I'm a bit confused by what does one mean by a gauge generator? If they're not of the same size, because the whole sort of machinery you said when you were talking about perturbation theory was that they had to be the same size. So now,
so you can still just use the exponential map to define the transformation of a tensor.
okay, so,
on
so
a
it's
manifold.
literally just a coordinate transformation that has its I components of what eta squared and its 0 component eta
Yeah.
cubed, and okay.
Yeah.
But it's not a gauge transformation that would be a valid perturbation theory transformation.
No, it's a different.
Cool. Okay.
This kind of gauge transformation you can only is a post-Newtonian gauge transformation, and in fact you can think about the fact that the spatial gauge transformation is of one order eta larger than the temporal one, as again being related to this small velocities situation, small time derivatives, and the way that information is propagating differently because we change the structure of the Einstein equations to Poisson.
Mm-hmm.
Make sense?
Yeah.
Okay. Right. So now we're going to have the worst slide yet, which is the slide where I write down the structure, the explicit structure of all the gauge transformations. But this is where the results fundamentally come out of. So applying that exponential map, you can just write down the behavior of all of the separate components of the metric under gauge transformations. So again here, that's just what they are. This will be well known to people who work in perturbation theory. These are just the standard first order gauge transformations.
Right. There's some new symbols that have showed up, the curly H and the zeta.
So curly H is just the Hubble factor, just a conformal Hubble factor.
Right. So that's the normal one, but divided by an extra factor of A or something like that. The derivative with respect to conformal time.
Yeah, just in conformal time. Yeah. And then the zeta is just again we've just decomposed the spatial gauge generator chi I into some part that is a derivative of a scalar and some part that's in inherent vector. So you can, but it's just so in fact I could show you in the paper. It's just not it's just a redefinition. Don't worry about it. But the point here is that in this cosmological perturbation theory scenario, firstly, the conformal Hubble factor doesn't have a size. It's just the same size as all the background quantities. And the gauge generators, they're all of size epsilon. So this set of transformations looks like something which is of size epsilon going to something which is of size epsilon plus something which is of size epsilon. Make sense?
Yeah.
Okay. So the post-Newtonian gauge transformations, they look like this. And firstly, you'll notice that some of them are slightly different.
Yes.
But secondly, what I want you to notice is that if you just look at that gauge transformation for phi, the size of phi in the post-Newtonian expansion is eta squared. Now, the size of the next object, which is curly H multiplied by chi naught, chi naught has size eta cubed. And the conformal Hubble factor here, this has a time derivative in it. So it's a dash or a dot divided by a. So that will also have an extra factor of eta. So you've now got a gauge transformation that looks like something like eta squared plus eta to the power of 4.
Just to clarify things, the curly H is derivative with respect to conformal time, and conformal time is just like ADT or something like that, right?
Yeah, exactly.
So, and the A is not playing any changing and scaling part here?
No.
Okay.
No, it's just the fact that there's a time derivative of that A.
Okay.
That's where...
But a conformal time derivative is the same as a time derivative for the scale counting business.
Yeah, exactly. You can just do the coordinate transformation and the behavior carries over. It shouldn't matter.
Okay.
But the point here is that with this gauge transformation, you've got something that looks like something of size eta squared being added to something of size eta to the power of 4.
Right.
And in fact, what that's telling you is that at least when you look at leading order, which is size eta squared, that quantity phi is gauge invariant, and that you can only modify higher order behavior using gauge transformations of phi. And that's quite strongly in contrast to the situation in cosmological perturbation theory, where your gauge transformation looks like epsilon plus epsilon.
Yes.
Right. So also you can see that the psi is just gauge invariant. It's just a gauge invariant quantity at all orders. This post-Newtonian expansion. The two other scalars, B and E, they obey, however, the same transformation law, although the magnitude of the quantities is different. So in cosmological perturbation theory, it's just epsilon plus epsilon for B and E. In post-Newtonian gravity, B has characteristic size of eta cubed. So you have something which is eta cubed plus eta cubed, and E is the same.
Okay.
Now you can also work out what the gauge transformations of all the matter variables are. Sorry, I really do apologize for this slide. It's just like a ghastly slide.
Hopefully the fact that this is like permanently stored somewhere, if people find this boring, they can skip through it, and if they don't, they can rewatch it, rewatch it, and rewatch it.
Just click pause and convince yourself with a pen and paper that what I'm saying isn't complete nonsense.
And 3 months from now, come back and watch the rest of the
video. Okay, so, and again, what's happening in the matter sector is really quite considerably different. So in cosmological perturbation theory on the left, you've again just got these gauge transformations of the matter perturbations, which is like delta goes to delta plus some epsilon quantity. So it's just like epsilon plus epsilon. And the same for the velocity and the pressure. But in the matter sector in post-Newtonian gravity, so I'm just writing rho there equals mu and then 1 plus pi, where pi is like some specific energy density.
Okay, those are the definitions of mu and pi.
Yeah, exactly. So pi you can think of as just being like some higher order correction to the energy density. And mu is just like the leading order part of the energy density. So mu on its own is eta squared. Pi is eta squared, but pi times mu is eta to the power of 4. So it gives you like the higher order part of the energy density. But you'll notice that at leading order, mu, p, and vi are all gauge invariant. And again, this is now like sharply in contrast to the case in cosmological perturbation theory.
Can I ask a question that is a little tangential here, but is post-Newtonianism, like, is there a unique gauge choice, or is there some freedom there as well?
There's freedom.
But is it unique as in everything on the right-hand side here has to be the case? There's no like other way of doing post-Newtonianism where the stuff on the right isn't.
Yeah, so everything on the right-hand side here is this is just an arbitrary gauge transformation in post-Newtonian gravity. Like this is just if you made the most arbitrary possible transformation, this is what you would.
And then the gauge freedom is in exactly what psi naught is.
Exactly. Yeah.
Subject to the fact that it is of the size that.
Yeah.
Okay. Right.
Exactly. Right. So what I'd like to do now is if you've got any way of keeping that on the screen so people can use it as a reference, that would be great. Because what we're going to do now is we're going to look at some specific choices of psi naught and all of the other things in cosmology, in cosmological perturbation theory and post-Newtonian theory, and we're going to see whether or not these gauges that are realized in cosmological perturbation theory can be realized in post-Newtonian theory.
Unfortunately, I don't have the pre-existing Zoom knowledge, and either we pause the recording and I play around and try and work it out, or we just carry on and we rely on the viewer to, like, I don't know, take a screenshot or something. Let's just soldier on unless
let's just go for it then. So I'm gonna bring up the paper now and we'll look at our the first of our gauges. So right, just work out how to screen share. Got it?
Yeah. Just seeing if there's a way of having a two-panel.
Look, the equations are in the paper.
Okay, awesome.
So
awesome.
We're all good.
No problem.
Okay, so let's look at this. The first specific gauge choice that rocks up in cosmology. So spatially flat gauge. So this is very commonly used. I think people use this in inflation quite a lot. So this is just defined by a choice. You choose your gauge generators psi naught and psi I such that the following relationship is true, which is psi equals E equals Fi all equals 0.
Right.
And it's quite easy to see if you look at the set of cosmological perturbation theory gauge transformations. For example, just look at psi here. So that's in 38.
Yep.
You can see that if I chose chi naught equals to psi over h,
Yep.
then I would be forced to set psi goes to 0.
Yeah.
Yeah?
Yeah.
Makes sense?
Yeah.
What happens if you try and do the same thing in post-Newtonian gravity?
Good question.
Well, psi is gauge invariant.
Okay. Yeah. Yeah.
So you can't. So
Right.
if you choose psi equals 0 in post-Newtonian gravity, then you are setting psi equals 0 in all post-Newtonian gravity coordinate systems that you could reach via a gauge transformation. So those two coordinate systems that you defined in cosmological perturbation theory and post-Newtonian gravity, if you extend the one from cosmological perturbation theory down to these scales where you should be using post-Newtonian gravity, those coordinate systems are no longer close to each other.
I see.
Does that make sense?
Yes, that makes sense. I think I'm suffering connection problems.
Hello? Still there?
Yeah. You said
Okay.
I'm suffering some sort of mild connection problem at the moment.
Okay, cool. Yeah, I just lost you for a sec.
Cool. Yeah, you said, does that make sense? And the answer was yes.
Okay, yeah. So if it's a gauge invariant thing and I set it to 0, it's 0 in all coordinate systems that are close. So that's bad. And so you can already see, I think, from the large number of quantities in the post-Newtonian theory that were gauge invariant, specifically the leading order energy density and the velocity.
Yes.
That setting just choosing nimbly some gauge transformation to get some desirable properties in the metric is going to be a little bit more tricky than it would be in the cosmological perturbation theory scenario. So another one is, for example, synchronous gauge. So this is used in numerical studies really frequently. But it turns out that, again, you would be forced into choosing the 0-0 component of the metric to be 0 in that gauge. I mean, that's what it means to be synchronous. And you just can't do that in post-Newtonian theory because you'd be choosing a gauge invariant quantity to be 0. Same thing happens in many other gauges. The M-body gauge. So again, this combination of peculiar velocity plus B is what you need to be 0. So you can't explicitly do that for the M-body gauge because, again, you're just choosing some gauge invariant things to be 0. However, it turns out that there is a modification of the M-body gauge called the Newtonian motion gauge in which you can do these things. But I think the important one to look at is longitudinal gauge, which is kind of nice because it's probably the most familiar gauge that everybody who learns this stuff in perturbation theory uses, otherwise known as Poisson gauge. And Poisson gauge is defined by the choice B equals E equals 0.
Okay,
and if you remember,
B and E were the two ones that show up in the naught I components of the metric.
Yeah, exactly. And if we look back at this structure of the gauge transformations for B and E, so that's 55 and 52.
Yep.
That's the post-Newtonian transformation of B and the post-Newtonian transformation of E.
Yeah.
And then if you look at the transformations in 38, which are the cosmological perturbation theory versions, magically those two gauge transformations remain unaffected. So you can see that I can realize the longitudinal gauge.
But just a quick question, because even though the form, can you go back to the Newtonian gauge, post-Newtonian gauge transformation? So it's not enough that they look the same, right? They have to also be the same order, and I guess they must be the same order.
No, they're not the same order. So in particular, this B is slightly smaller. So this is eta cubed. Whereas
but I guess zeta dot and psi naught are also eta cubed.
Yes, exactly.
That's
Yeah.
the
So
crucial thing.
you,
So yeah, E
yeah,
is a different size to B, but E and zeta are the same size.
yeah,
Because
exactly,
the problem
exactly.
with phi wasn't that it looked different, even though it does have this final term, but the problem was that the terms are of different sizes, right?
Yeah, exactly. The problem is that the leading order part, so phi goes to phi plus stuff, but
Yeah,
phi is eta squared, and all of the stuff is eta to the power of
yeah,
4.
yeah.
That's some, so it can only affect all of the sub-leading order behavior. Whereas in 52 and 55, all of the terms on the right-hand side are the same
Same
size.
size. Cool. Okay.
And that means that you can equivalently choose longitudinal gauge in both the post-Newtonian expansion and cosmological perturbation theory.
I see.
Which means that if you wanted to, for example, do some calculations on large scales using cosmological perturbation theory and Poisson gauge, and then try and extrapolate things down to smaller and smaller scales where the density contrast might become large,
Yes.
you might still be okay, because your coordinate system essentially might you might be able to map your results onto some post-Newtonian
And why are you
calculation.
saying might rather than are, rather than you are okay?
Why am I saying might? Well, because they're difficult calculations. I haven't yet done them.
Okay.
And there are also there's a huge number of other problems with associated with trying to do these higher order perturbation theory calculations. So, for example, some people try and use renormalization type techniques to deal with large delta on small scales, and it's unclear to me, as of yet, whether or not there could be some renormalizing going on in the gauge or something like that.
You mean the sort of like effective field theory approaches and things?
Yeah, exactly. But naively speaking, it does look like longitudinal gauge is quite a sensible gauge to use if you want to do this kind of thing.
Yeah, okay.
So in
might be
particular,
okay rather than definitely won't be okay is at least an improvement.
Yeah, exactly. I would put it like this: not even might be okay, but there's no objection as of yet. There might be a sort of Rumsfeldian objection.
Okay,
I always feel like that.
Fair enough.
In science, but
and there's always the inhomogeneity averaging problem lurking in the background anyway. So
yeah,
no one's ever 100% okay.
Yeah, and so longitudinal gauge is great because usually it's quite nice to calculate things in longitudinal gauge as well, especially from a sort of pen and paper perspective. But it also turns out that there isn't.
Sorry, just quickly, this might be a bit of a tangent, so maybe we don't want to go down it. But my understanding of the papers that wrote these recent papers talking about the n-body gauge was that before those papers got written, everyone who was doing n-body simulations thought they were doing their n-body simulations in the longitudinal gauge. And those n-body gauge papers were saying, no, you're actually doing it in the n-body gauge. Is that a correct understanding of those papers, or am I way off? My next talk should be with one of them?
No. I think you are onto something there. Again, I did read those papers, but it was a while ago, so I wouldn't quote me as 100% accurate.
Okay, sure. But so now when you...
But that was the original thrust of the n-body gauge. But the point about what they were trying to do was they were trying to extract relativistic results from Newtonian simulations.
Yeah.
That was kind of that was the sort of the key point, is that they were trying to access some relativistic information without having to go to the full difficulty of doing a full relativistic simulation, which is extremely difficult. But initially, when people did that, I think you're right in saying that they were assuming that all of their Newtonian simulations were operating in longitudinal gauge. But yeah, there was some, I can't remember the specifics of it, but there was some specific technical problem that did occur between trying to translate results between all these short scale Newtonian nonlinear simulations and the large scales.
I have to leave that as this is as good as we can get
for further research.
But
unfortunately, it looks like you can't really realize an n-body gauge in post-Newtonian approximation. So although although the n-body gauge was designed to map results from some nonlinear short-scale simulation onto sort of some cosmological perturbation theory corresponding large-scale behavior, it can't be realized in this post-Newtonian approximation. But it does turn out that there is a modification to an n-body gauge that you can do, which is the Newtonian motion gauge. And this problem was already known, and it was already fixed by Fiedler and Wands and I can't remember, but in their papers on the Newtonian motion gauge.
And I think both of those people were on those original n-body gauge papers. So it was fixed by the people who,
no, all of them, they knew about this stuff. And they designed this specifically to deal with those problems. And the idea of the Newtonian motion gauge is it's a more complicated gauge choice than let's just choose psi equals 0, or let's just choose delta equals 0, or something like that. They say, we want to consider some variables, which we don't yet know what they are, such that the variables satisfy the nonlinear Newtonian equations of motion.
I see.
Now, because the Newtonian n-body simulation solves the nonlinear Newtonian equations of motion, you have the solution to those equations. So if you can then work out what the variables you needed to choose were such that they satisfied those equations, then you magically extracted some relativistic results out of your nonlinear Newtonian n-body solution, which is really is an absolutely amazing idea, and a really promising way, I think, to try and get around all of the technical difficulties associated with this kind of subject. But so it's
I guess just as another interruption, and there's obviously another way one can go about this, which is to modify what you do in your n-body simulation such that you don't have to jump through quite so many hoops. And there are people who've sort of gone down that path a little bit. Is this G-evolution?
Julian Adamek in my group did G-evolution, which is precisely a n-body simulation where gravity is weak field general relativity instead of
purely the Poisson equation.
Instead of purely the Poisson equation. Now, obviously, the difficulties are huge in doing this thing, and G-evolution really requires to run on some incredibly expensive, like state-of-the-art computing software. But the results they've got are pretty remarkable. But for example, if one can solve the technical difficulties associated with the Newtonian motion gauge, it might be possible to, in some circumstances, bypass doing a full run of G-evolution and instead just run a Newtonian simulation and then just post-process the results to work out what all of the corresponding relativistic results would be. And that's obviously a very attractive proposition. And it turns out that you can realize this Newtonian motion gauge in both the post-Newtonian approximation and the cosmological perturbation theory approximation. I mean, and it's not not surprising in such a sense because it's precisely what it was designed to do.
But I mean, it's good that it does that.
It is good that it does that. Now, the derivation's a little tricky, and so I'm not, I think, going to go into it in a huge amount of detail, because if you want to follow the derivation, you can just read the paper.
Sure. I think what you've said about it so far is going to be very insightful for people already. So,
but I think the one important thing that you should pick up is that the way you realize the way you can realize the Newtonian motion gauge in both circumstances. Firstly, you're required to have any pressure perturbations be negligible. So you can't. You're restricted to sort of usually to dust situations. if you do this. But secondly, the difficulty is not then in solving the nonlinear evolution, which you just do with a Newtonian simulation,
Right.
but in post-processing the results of that simulation. But what you can do in this equation 89, you see equation 89?
Yep.
It turns out that all of the relativistic quantities that you need to get out, you can get them out by solving equation 89. Now, equation 89 is a bit of a complicated thing. A few different complicated defined things go into it. It's a non-local equation, and the non-locality, I think, results because of the Poissonness of post-Newtonian theory. So, but all of the things that go into equation 89 are just standard defined things in literature in post-Newtonian theory, and you can get them directly out of n-body simulations.
I have to ask what phi 7 I is. Why is there a 7 there? That's just so amusing as a non.
You can in post-Newtonian gravity, you often define these things called like auxiliary potentials. Okay,
and this is usually the 7th one of them.
This is the 7th one of them,
okay.
and they're just useful.
Right.
And they often allow simplifications, and often they obey lots of relations that allow you to manipulate them in terms of each other.
I see it's defined in equation 91. Although, I mean, I have to assume that gamma... and gamma is defined there as well. Okay.
Yeah. So, but yeah, fine. It's just one of these kind of standard quantities that crops up in post-Newtonian gravity. But the point is that you can build these things directly using the stuff that comes out of an n-body simulation.
Right.
So all of the stuff that goes into 89 is just the output of an n-body simulation. So if you can then solve 89 as well, then you're in business and you've got everything.
Yeah. Okay.
And presumably, I mean, I'm no expert, but it's just an ODE.
Yeah, that's what I was thinking.
It is non-local, so it shouldn't be too much of a challenge. And again,
I mean, yeah, maybe no more of a challenge than the original n-body simulation, but yeah, okay.
Yeah, so if just to clear up about phi 7, you can see that in F, which is the source function there, phi 1, phi 2 for all of these things are cropping up.
Okay.
But yeah, the point I wanted to make is that they shouldn't be too scary, because they are things that are just kind of well known in the post-Newtonian literature, and you should be able to just build them directly out of the box.
And so maybe I'm jumping to the conclusion now, but is this now something that, like, someone doing, who is going? And just tell me if you want to wait to answer this question. But which observational things are going to need to do something like this? Is it like large-scale CMB lensing, or is it correlation functions over more than 100 megaparsecs?
So yeah, or weak lensing, large-scale correlation functions, bispectra on large scales, all this sorts of stuff. Anything where you might want to calculate some relativistic effects is kind of the applicability.
Okay.
Also, I think it's important to do these kind of calculations because, I mean, traditionally the assumption in cosmology is like relativistic effects don't really matter because they're all small. But the reason they're all small is because everybody calculated them with perturbation theory, which kind of assumed by default that they were small out of the box. If you do things just a little bit more like rigorously in this way, and look at also, if you look on small scales where some of the quantities that you assume to be small in perturbation theory might not necessarily be small, then if you calculate things like this and it turns out that all of the answers on larger scales still are small, then you've like justified the approximation that everyone else made. And if they're not small, then you've got a way of calculating them anyway.
Yeah.
So it's kind of like philosophically a bit more happy of a situation to be in.
Yeah. I mean, I definitely wasn't meaning to call into question how useful your work was as
no.
It was more just if someone does end up listening to this and they are like calculating weak lensing or something like that, should this be something that they'd be implementing into their pipeline?
I think weak lensing is particularly an area where this kind of thing might be interesting, because it's where you have coupling between large scales and small scales.
I see. Is that because essentially the light that's being lensed has traveled over a very large distance, but the gravitational object doing the lensing might be quite small?
I don't know. It's
Okay.
because there's a convolution over Fourier modes in the expressions that
Yeah.
I've seen in papers. I couldn't give you a physical intuition, but I wonder if that might be the case. Like,
okay, yeah, that's a satisfying, honest answer. That's cool. Yep.
So yeah, I guess that kind of wraps up the technical detail in this.
So do you want to maybe try and quickly summarize it, or maybe I can try and summarize it from what I've gotten, and you can see
interesting for you how much you picked up.
Yeah, and what misconceptions might have leaked in that we can cut in the bud, nip in the bud right away. One can do things with perturbation theory, and it's going to be totally valid so long as everything does remain small. One can do Newtonian simulations, and that's going to be totally valid so long as you're doing things on shorter distance scales and never want to ask questions on a maybe greater than 100 megaparsec scale, which, almost everyone is asking questions on greater than 100 megaparsec scale nowadays. The effects that come in on greater than 100 megaparsec are to do with relativistic effects. So there's this issue of how does one take Newtonian stuff or post-Newtonian theory and match it to the larger scales, which one can calculate using perturbation theory. When one looks at how, so there's certain coordinate transformations that one can do within the post-Newtonian world, and certain almost any coordinate transformation you can do in the no, that's not true. There's certain coordinate transformations you can do in post-Newtonian and certain coordinate transformations you can do in perturbation theory, and they have different scalings, so different requirements in how that can be done. And it turns out that there's a subset of each, essentially, that are valid in both, and this is the longitudinal gauge is one such example, and post-Newtonian theory is another such example. But synchronous or n-body gauge are not examples where they're totally valid perturbation theory gauge transformations, but they're not valid post-Newtonian ones. And so therefore, if someone wanted to use post-Newtonian theory to interpret something in that gauge, something's going to go wrong because you've set stuff to zero that post-Newtonian theory won't let go to zero.
Or particularly if you wanted to ask questions about cosmologies where there were large density contrasts on small scales, then things are going to go a bit wrong if you try and extrapolate perturbation theory calculations down into the nonlinear regime in those gauges.
And I guess the longitudinal gauge, whilst it works for post-Newtonian theory, has whatever the problems it has that made people write these n-body gauge papers, that it doesn't actually quite match onto what n-body simulations are doing. But this post-Newtonian gauge does.
I think that, again, don't quote me on this, but well, it's just kind of self-defeating since we're literally recording a video. But I think that the difficulties with the n-body gauge were to do with the n-bodiness of it, and because when we defined our longitudinal gauge here in a situation where you're modeling a perfect fluid, so I think the difficulties arose from the fact that it was a thing that was dealing with n-body simulations and had stress energy tensors that were like that, rather than rather than something that was wrong with the longitudinal gauge, because the key thing about longitudinal gauge is that it is working perfectly.
Oh yeah, sure. Yeah, I wasn't meaning to imply that. The longitudinal gauge was wrong, just that it's not what the n-body simulation is solving.
The longitudinal gauge is wrong.
No, I mean it's
the gauge that everyone uses.
It's not even that synchronous gauge is wrong. It's just that It doesn't.
It
It
means
isn't
something.
realizable within post-Newtonian theory.
Yeah.
And the longitudinal gauge is realizable within post-Newtonian theory, but may not be what an in-body simulation is solving.
Yeah.
And
Yeah.
the post-Newtonian theory is what an in-body simulation is solving and is reachable within post-Newtonian. Yeah.
What a Newtonian n-body simulation is just solving the Newtonian physics only, no relativity. Because the post-Newtonian approximation is giving you some higher order relativistic corrections.
Yeah. My brain and mouth were disconnected because post-Newtonian theory was on the screen. It was that particular gauge that, like, it was a few pages above this.
The Newtonian motion gauge.
Newtonian motion gauge. That is what my brain thought my mouth was saying, and it definitely wasn't what I was saying.
Newtonian motion gauge.
So the Newtonian motion gauge is realizable within post-Newtonian theory and is what n-body simulations are solving.
Yeah, exactly. So cool. as long as you can solve that one ODE that inverts the choices of all the different variables that you need to make, then if you solve an n-body simulation, you can get the relativistic answers out from this Newtonian motion gauge.
I guess if you were careful when you were solving that ODE about what you wanted to extract from it and what quantities you're expecting are small or irrelevant, you might be able to simplify it significantly without trivializing it down to back to exactly what the n-body simulation. Where rho is rho and v is v instead of being.
I expect that would be the case as well.
Yeah. Oh, cool. So what were the two things you wanted people to take out of this, just to repeat it so everyone who's made it this far can remember?
Be careful extrapolating calculations from cosmological perturbation theory into situations where there are nonlinear structures, even sort of weakly quasi-linear structures.
Actually, also, sorry to interrupt you midway through, but could you want to just remove actually I can do it myself, the screen sharing, and we can see you again.
Oh yeah, sure.
There we go.
There we go. Two takeaways. Be careful doing calculations in cosmological perturbation theory and extrapolating them down onto scales where things are mildly nonlinear, because the gauge you may have chosen could be potentially becoming far away from other gauges. But there are gauges that you can choose where you won't encounter this problem. Longitudinal gauge is one, and Newtonian motion gauge is another. So that's the takeaway.
Awesome. So I think this has been about a little more than an hour, so hopefully not too long. But the fact that people can take it in bite-sized chunks, maybe it's better. But maybe I need to work on other things. Anyway, so one last question. Just if you want to quickly go, what do you think is interesting in cosmology that isn't your own research at the moment?
Dark energy. I'd love to get into dark energy.
Okay.
Yeah.
Cool.
I mean, it's the most interesting questions are always the ones where the modeling is bad, and the modeling for dark energy is really bad.
Yeah. Right? Whereas with inflation or dark matter, there's heaps and heaps of models that could be correct, and we just don't know which one is the right one. With dark energy, there aren't really any that are good.
Yeah. But also, I mean, inflation to me seems like, in some sense, slightly better motivated than dark energy. Like dark energy, like inflation, as well as solving the traditional problems, inflation gives us a picture for the formation of large scale structure in the initial conditions, which makes it such a compelling physical theory. Whereas dark energy is basically just like a big question mark that says, oops, something's really wrong. Dark energy is the big problem. I'd love to work on dark energy.
Cool. I think we can leave it at that. I might click the end record, and then if you want to we can have a quick post-mortem if you want. Cool. Thank you, Kit.
Cool.